Alrighty, today's problem is back to a nasty one. It's quite fun, there's lots of symmetry, but yeah, it is quite challenging. So let's have a look at it. We're solving sin x equals a number. The purpose of this question is to solve it without the graphics calculator, or without a calculator full stop, but if you do put the right hand side into your calculator, you'll find that it equals 1. So in essence, we need to prove that that right hand side equals 1. Okay, a hint if you would like one to get you started. If you don't, then pause and try it yourself without the hint. It's quite a useful hint. We write everything in the right hand side in terms of 12 degrees. So 48 is 60 minus 12 and 72 is 60 plus 12. The not so obvious one is that 54 is 90 minus 3 times 12. So yeah, those rewriting the right hand side in that form helps us. Okay, solution. With our reformed right hand side, we use the compound angle formula for the 60 minus 12 and 60 plus 12 expressions, which seems obvious to do. What isn't as obvious is that tan of 90 minus something is equal to the cotan of that something. So this term where it says 1 over tan 3 times 12, I've used this kind of concept here that if we have a triangle and we take the tan of theta, then it's going to be the cotan of 90 minus theta, depending on what angle you use. If you use the bottom angle and you work out the cotan of it, that would be the same as working out the tan of the top angle, as they're reciprocals of one another, cotan and tan. Okay, so that first thing gets rid of that 90 part. You can't use the compound angle formula when there's a 90 degree. We talked about this in a previous video because tan of 90 degrees is not defined. Okay, then the next formula that I'm going to make use of is to get rid of that tan 3 times 12 thing. That's a triple angle. We don't have a triple angle formula, but we have the double angle formula and we have a compound angle formula. So using the compound angle formula, because we don't want to go into 1.5 thetas, we are going to have to use it twice. We use it once for the theta plus 2 theta business, and then we're going to get the tan 2 theta and use the double angle formula again. You're going to have fractions over fractions, do a little bit of simplifying before the next step. The next step, I've done a heap of simplifying. The first thing is the tan 60 is root 3, so wherever there's a tan 60, it's just become a root 3. I've taken the last term and put it next to the second term so that we can see there's conjugates there, top and bottom. And then the tan 3 theta stuff is upside down because we wanted cotan of 3 theta, and that's the last term in the expression with a bit of factorizing done. And then you'll notice that everything on the top appears on the bottom as well, so therefore that equals 1. And so we're solving sin x equals 1, and they are our answers. That's the general solution to the equation. Okay, for an extension problem, you're going to help me out. The first person to send me a solution where this is used will get the prize. Haven't done one of these prize collecting questions in a while. Can you show that right hand side equals 1 just using 24s instead of 12s? And this is what I tried, and I abandoned it. I thought, okay, well, 12 is half of 24, 48 is double 24, 54 is 30 plus 24, and that's okay because we know the 30 degree angle. Tan of 30 is a nice number, and 72 is 3 times 24, which is, yeah, that's okay. It's a triple angle, but we've now seen how to work with that. I got it all the way down to this bottom expression, which actually equals 1. I've checked on the calculator, so there's no errors, but I can't get that. I can't prove that that's equal 1. I'm either missing something, or it's because that square root expression is messy. Square root expression came from the half angle formula, so the double angle formula rearranged, and it's just a bit messy, and I can't see how to prove that it equals 1. So if you can help me out, definitely a prize